Welcome to Module 12. In this module, we'll discuss direct static code injection attacks. A direct static code injection vulnerability is a special instance of the PHP injection flaw. It occurs when users are able to affect the data passed to a file stored server-side, where the file is further processed by a PHP interpreter. Let's take a look at an example designed to illustrate this. The file contains a simple script which logs visitor parameters. A file is opened server-side. Next, the script writes data to the files such as a user agent, session length, and IP address. Date and time is generated by a PHP interpreter, and IP address is referred by a web server, which means that both values will have a specified format. User agent, on the other hand, may hold any format. As you can see, the input is unfiltered and is logged directly to a file. Let's now take a look at a file used for browsing the logs. Our database file, which holds visitor records, is added to log_view.php. The include function parses the file and executes the embedded PHP code. You can see here sample database entries. Let's see now how the script works in practice. As you can see, the file has logged an entry which contains our session history, the IP address, session length, and user agent. Let's now use the Live HTTP Headers add-on, which enables you to modify HTTP requests and also makes it possible to alter the user agent string. First, open the page again so that Live HTTP Headers may capture the request. Generate a new request based on the captured query. As you can see, all data can be freely tampered with before it's sent to the web server, giving us a chance to manipulate the headers. Let's try to put the following record into our database. As you can see, no error message has been displayed. Let's take a look at the database. You can see here our PHP string. Let's find out how the file will affect the behavior of the log_view.php script. The injected PHP code has been executed as predicted. What could be done to evade the exploitation of these vulnerabilities? First, bear in mind that parameters like HTTP user agent are user input and cannot be relied upon, as they may hide malicious scripts. Second, remember that the include function is used for including files that contain PHP code. Since our intention here is only to display the contents of the file, the include function is non-essential. You could replace it with the echo file_get_contents call. Let's see how this affects the functioning of our script. As we can see, the PHP code has been displayed but has not been executed. Is this enough to secure ourselves from an attack? Unfortunately not. If the code is displayed only, a hacker may inject an image code instead of PHP. resulting in an XSS attack. Let's try to simulate this scenario. To do this, make slight changes in the request. Our database now contains HTML code with JavaScript. Let's see if this affects the reading of logs. As we can see, the JavaScript code has been executed, which makes this an instance of a cross-site scripting attack. These types of attacks will be discussed in greater detail in Module 14. For now, remember to never underestimate the risk connected with inadequate user input parsing. We could use the HTML special cars functions to convert characters used in HTML tags into entities that are displayed but not interpreted. Let's see how this script will behave in this situation. Clear the added data from the database and execute another HTML request. As you can see, special characters have been converted to HTML entities. They are displayed on the page, but JavaScript code has not been executed, which means that we've managed to successfully protect ourselves against a code injection vulnerability. That's all in Module 12. Thanks for your attention, and see you in the next module, which will focus on SQL injection. See you there. Welcome to Module 13. This module will focus on SQL injection. Many web applications today make use of databases to store data. If that's the case, SQL queries need to be an integral part of these applications. SQL queries are used to retrieve and pre-process specific data stored in a site database. These queries are often generated dynamically using input parameters passed through the GET and POST methods. An SQL injection vulnerability occurs when users can manipulate the final content of an executed SQL query. Take a look at a sample script designed to illustrate this. The first page we'll discuss is a simple login form which first connects to a database. A form is displayed. If the form is passed to a script, an SQL query is generated which retrieves appropriate database records for the submitted user credentials. If this operation is successful, an appropriate message will be displayed. If it fails, a corresponding message will appear to the user. Let's see how the script works. Here's the login script. We have successfully logged in because the database contains records for the admin user holding the test password. Now enter invalid user credentials. As expected, the login has failed. Notice that user-supplied data is not filtered or validated in any manner. This means that users have control over the result SQL query. Try to think what a potential attacker could do in this situation. Let's see what will happen if the following data is sent. While these credentials are certainly invalid, altering the SQL query results in a successful login. Take a look at another example. We can see here a simple application which loads articles using an identifier passed through GET. The ID1 value holds a sample article with the content, test article. Let's see what will happen if we change the query slightly. Since no content has been displayed, we might assume that the application is vulnerable to SQL injection attacks. Let's try to verify if this is the case. Add in a string which will constitute an invalid identifier, but which won't change the behavior of an SQL query in which it's placed. As we can see, the approach has worked. This confirms our suspicion. We may freely alter the end of an SQL query. Still, we need to find out which table the query works and how many columns the table has. By using the order by keyword used to sort records, you may discover the number of columns returned by an SQL query. Order by might be used to specify the number of a column by which columns will be ordered. If the number is greater than the amount of columns returned by the query will be incorrect and won't return the requested result. If we submit 1 as the specified value, the columns will be sorted by the first column, which should always exist. Confirm this by entering the following address. Let's now try to specify as the value a number so great it probably won't correspond to the number of columns returned by a query. In this way, we'll make sure the query is working as predicted. As we can see, the query indeed has not contained 100 columns. This is why no content has been displayed. The database engine has interpreted the query as incorrect. Now, let's submit several values to discover the exact number of columns. As we can see, the query fails with the parameter of 10. It does not work with 5. The operation is successful with the number 2, so we know that there are at least 2 columns, but no more than 5. Let's try with 3. The query fails for this value, which means that it returns exactly 2 columns. We'll use the union function, which allows you to combine result sets of select statements from both sides. Union requires the statements to have the same number of columns. The attempt has succeeded. We now know that the database supports the union function. None of the values we passed has been displayed. The reason for this is that the page only displays the first result set, while the ignored second result is the one which was added by union. Once we add the AND 1 equals 0 string to the first request, we'll cause it to return no results, and so our request which is glued by union becomes the only request. This time, one of the numbers we passed in a select statement has been displayed. The displayed number 2 means that the value of the second column is displayed on the page and may be used for passing data we'd like to retrieve from the database. Let's use several standard functions. The user function returns the name of the current database user. In this case, this is the test user working on a computer where a database server has been launched. The version function returns the version of the database. What else could be done in this situation? Starting with MySQL 5, the software is equipped with Information Schema, a special database used for storing information on the structure of all other databases and tables, which can be accessed by users. This is a form of a database reflection mechanism. The first way of using it in SQL injection attacks entails the discovery of table names. Select Table Name from Information Schema in Tables, which contains information on all tables viewable by the current user. The head of the table contains the system tables as well as information schema tables. To discover other tables, use the limit function, which allows you to set a result range. "100 is too big," while 20 still shows the system tables. The 30 value has returned the user's table. The name looks promising. We'll now use the columns table from the information schema. As you can imagine, the file contains column names viewable by a current user. Add a condition which specifies that we're interested in user table columns. Column name is the name of a database field which contains column names. As we can see, ID is the first column name. The second is disabled attempts. The next is login, which looks interesting. The fourth column is pass. In this way, we have specified a current user and can access the user's table, which contains the login and pass fields. Using this information, we'll be able to display the contents of the table. As you can see, the first record of the table defines administrator. We can also display the pass column to see the password unencrypted. To prevent this, we need to remember several steps. The first step is to put all parameters in quotes. While this isn't a security measure per se, it is the basis allowing for the data to be filtered further. In the case of this script, the identifier is always a numerical value. Using the intval function, we can make sure that the return value will always be a number. If a string is placed at the start of a function, the 0 value will be returned. Let's see how this works in practice. As we can see, the attack has failed. What can be done if the query has to be made up of strings? Notice that if attackers are to manipulate the content of an SQL query, they need to use quotes. You can now filter input data for quotes using the MySQL Real Escape, Preg Replace, Add Slashes, or HTML Special Chars functions. The HTML Special Chars function can also help you protect yourself from XSS attacks. Let's see if this works. As you can see, this time the attack has failed as well. Let's also see what could happen if a user working with a database has rights to operate on files. The rights are set while creating users or granted by administrator. A normal user very rarely has file operation rights, but they are enabled by default for the root user. Use the load file function in SQL, which enables you to load the contents of the file. As you can see, the contents of PHP-ini have been displayed. The function enables users to access all files to which the current database server user has access rights. Logging data to a file is also possible. First, let's prepare a string which will be saved in the website directory. A PHP code which calls the php info function. The directory contains only 2 files. As you can see, a test PHP file has been created after sending a request. You can even run it. The value 1 comes from our select statement, as the select into out file function logs all columns returned by a query. This won't do much to stop an attacker from saving the file with PHP code. So how do we protect ourselves against SQL injection attacks? As you can see, if database user configuration is poor, file operation becomes possible. Remember, you shouldn't work with your database using the root account, as the root user has full file rights, permissions to operate on files, and unlimited access to all database tables. It's good to disable file operation permissions while creating new database users. That's all in Module 13. Thanks for your attention, and see you in the next module, which will focus on cross-site scripting vulnerabilities. Welcome to Module 11. In this module, we'll focus on the PHP injection vulnerability. This vulnerability occurs where a user has the opportunity to execute a malicious PHP code by modifying the parameters passed to a web application. This situation could take place if input parameters are passed into the PHP functions that allow the direct or indirect PHP code execution. The first function group are the include family functions, include, require, and require once, which serve to include and parse files containing PHP code. The second function of this type is eval, which parses and executes provided strings. The third function is preg replace, used to verify regular expressions. The parameter e could be passed to this function, allowing for the execution of PHP code passed in a part of a regular expression. As the two latter functions are rarely utilized in standard web applications, we'll focus on the first function. This sample source code will help you understand the concept. You can see here a simple PHP script which utilizes the user-provided variable site for specifying which page should be added to the include function. The content of the website is provided depending on a specified file. As we can see, user-provided parameters are not filtered in any manner. A user has virtually full control over the file name. Let's see how this works in practice. We can browse the website, and as we're doing so, the file names in the address bar are changing. Assume that a hacker has successfully uploaded a file which contains a PHP code to the server. Perhaps you're a bit skeptical. After all, uploading PHP files is certainly disallowed by the site, or the service doesn't accept any files from users. It's common, though, that websites allow users to upload avatars, pictures, and other image files. Let's see if an attacker can still smuggle in a malicious PHP code if files are checked for correct format. You can see here a specially crafted image that looks like a normal JPEG file. Its content is displayed. All image functions will interpret it as a correct image file. But let's take a look at what's hidden inside. As we can see, PHP code has been embedded in the image. Let's try to pass it in the address bar. As you can see, the script injected into the image has been executed. But even if an application has disabled uploading images, a hacker could still use other vulnerabilities to launch a PHP injection attack. File operations in PHP, like including, allow not only direct file references but also enable protocols such as FTP, HTTP, and special data protocol. In the case of data protocol, it is possible to pass file content in protocol reference parameters since the file is generated on the spot. The data is encoded in base 64. Let's use an online encoder to generate an encoded string. Try to encode the following string, converting it into a base 64 string. Use special data stream syntax and paste the encoded PHP code. As we can see, the code has been executed. Let's try to think of how we can protect ourselves against this attack. The first solution is to modify the configuration of PHP ini. The Allow URL Include option might be used to enable or disable the inclusion of special files which are accessed through the protocols we've mentioned. After disabling the function, you need to restart the server for changes to take effect. As you can see, this time the attack has failed because the options were disabled. Attacks which utilize images are, however, still feasible. As you can see, the underlying cause of the problem is the fact that users practically have full control over the string passed to the include function. You can deal with this by adding static extensions to included files. By doing this, we can prevent an attacker from manipulating the extension. The image has not been included this time. Controlling extensions in this way is enough for PHP 5.3 and newer editions, but older PHP versions allowed the usage of special character %00. The null byte, or end of string marker, was placed in the target string passed to system functions, causing the extension included by a web developer to be dropped. Since this vulnerability was often exploited for attacks, while the need to include the %00 marker in user-provided parameters was rare, the character has been disabled. You can also specify a folder in which the function include will operate to prevent users from tampering with the beginnings of file names and disable special protocols. The next step is to use the preg replace function to remove the dot and slash characters, which makes it impossible for a potential attacker to control the inclusion path. Creating a list of files which can be included and blocking all other references seems like the best solution. If you can't implement this method, try to deter a potential attacker by filtering input. That's all in Module 11. Thank you for your attention and see you in the next module, which will cover the direct static code injection attack. See you there.